Hello, my name is Devanshi Patel, and I'm a senior at Holt High School. My research this year was on increasing the efficiency of iron catalyst reactions. Now, catalysts are anything that are used to speed up reactions, and they do that by lowering the amount of energy required to make a reaction go through. They are used in the modern mass production of things such as petroleum, cleaning products, and in this case, medication. The usage of ferrocenium catalysts or iron catalysts are brought up as a way to replace more toxic second and third row transition metals such as ruthenium, as less of the ferrocenium catalyst is required in order to go through with the same reaction. These reactions rely on the usage of propylylic alcohols, which are key ingredients for catalytic hydrogenation in the synthesis of organic materials. The two variables that I looked at are the solvent used in relation to the product yield, along with decomposition studies of different catalysts and solvents in order to produce a more stable reaction. Looking at it structurally, the image on the left is the catalyst that I used in the reaction experiment. It is ferrocenium tetrafluoroborate, and the box in black shows the actual ferrocene part of that catalyst. It is essentially a sandwich complex of the iron ion in the middle in between two organic ligands, which are essentially structures of carbon and hydrogen, and that forms the positively charged cation that is paired with the anion tetrafluoroborate in order to form the entire catalyst. These catalysts are key ingredients for propylylic substitution reactions in which it relies on the usage of a tertiary propylylic alcohol, a primary alcohol, a solvent, and of course the catalyst. Now in these reactions have a hydroxide group, as you can see boxed there, and that hydroxide group from the structure of the primary alcohol, as seen boxed in gold, is then replaced to form the product, as you can see on the very right there, also boxed out, which is the catalytic hydrogenation of the process in which the alcohol is substituted. For the reaction experiment or question one, a reaction was made with the catalyst, propylylic alcohol, primary alcohol, and solvent. That reaction was run for 2 hours at 45 degrees Celsius before it was analyzed. The decomposition studies, a solution was set up with the catalyst in either regular dichloromethane or nitrogenated dichloromethane. In some cases, a variable co-solvent was used as well, and that solution was placed in a sonicator to increase the solubility in order to make sure no particles remain, and then that solution was analyzed. The methods of analysis for the reaction experiment or question one is that it was analyzed with gas chromatography. Essentially, the percentage yield was determined with a small sample that was injected into the gas chromatography machine, and then that resulting peak was integrated to give up the percentage yield, as shown below. For the decomposition studies, it was analyzed with time-resolved UV-vis spectroscopy, in which decomposition was analyzed and the absorbance was graphed against time, and that linearized gave the rate constant of decomposition. In the image to the right, which gives the visible spectrum at each wavelength, at about 615 nanometers, so in that range as seen by the arrow, is where the ferrocenium catalyst absorbs light. So at that wavelength, the absorbance was graphed. Going to the results, these are the reaction experiment results. The one in silver is dichloromethane, so the standard in the laboratory, which had about 90% yield along with the other chlorinated solvent dichloroethane. What is surprising, however, is acetonitrile, which had almost 100% yield across 4 trials, and that is hypothesized due to its simple chemical structure. And that is supported by the fact that the two heavier solvents, dimethylformamide and dimethyl sulfoxide, had under 2% yield as its complex chemical structure overwhelms the function of the catalyst. Looking at the decomposition studies, there are 2 pairs of value. Looking at the top 2 pairs with the catalyst ferrocenium hexafluorophosphate, in normal dichloromethane, it has the following decomposition rate constant, but when that solvent is placed into a nitrogenated version, its decomposition rate is slightly lower. Now, if we look at the bottom here with this catalyst, in normal dichloromethane, its decomposition rate constant is actually very fast, but with the placement of the co-solvent HFIP, hexafluoroisopropanol, its decomposition rate constant is significantly lowered, making it the most stable architecture of the entire testing group. Now, the data suggests that the usage of a simpler solvent, meaning a lower molar mass and simple chemical structure, will increase the efficiency by stabilizing the catalyst and not interfering with its function, meaning that more product is formed at the end. From the decomposition studies, it is suggested that the inclusion of a nitrogenated solvent along with a co-solvent may also increase the stability of those catalysts in order to allow the reaction to run to its fullest before the catalyst function is decreased. In the future, I'd like to identify the ideal time and temperature for these reactions as those were kept constant, along with testing different alcohols used within the reaction. In the end, this data shows and suggests that the usage of simpler solvents along with nitrogenated solvents and co-solvents by increasing the efficiency of the reaction. The increased efficiency of that reaction means that more product can be made in the same amount of time, such that modern mass manufacturing processes can be faster and better for the consumer. By replacing more toxic transition metals with iron catalysts, that reaction is also thereby greener and better for the environment. I'd like to thank the following for their assistance with this project: Dr. Ike Bauer in the Department of Chemistry and Biochemistry at the University of Missouri St. Louis, Kelsey Jerkowski, Diva Talasila, and Ms. Jennifer Hess in Wentzville Holt High School. These are my sources. Thank you for your time.